All right, so now you finally get some practice what you've just suffered through. Okay, so what I want you to do, grab a piece of paper. Draw a single slit diffraction pattern. So in other words, just draw what you see on the screen. And don't be fancy, just do it. If you want to look back to the previous chapter or want to look at the book, I don't care, just single slit diffraction pattern. So draw that. Okay, something like that, right? And again, this is overexposed, all right? So this is super, super bright, the central piece here, and this is not so bright. It's really much, much dimmer than that. This is much, much dimmer, you know. This is much dimmer, that's much dimmer, okay? All right, now, what does it represent? The amplitude or the intensity? In other words, what do you see on the screen? Well, you see the intensity, agree? You see the intensity. Because, I mean, the amplitude has positive and negative. What does it mean to see something negative on a screen? I don't know. So you see the amplitude squared, you see the intensity. Okay, sorry to do this to you. Using under your diffraction pattern, draw a corresponding dot pattern. So take your pencil or whatever, and underneath this, draw a dot, a photon pattern. So pause your video and do that. It's going to take a while. Okay, so, you know, what can I do on PowerPoint, right? So you just want a whole bunch of dots here, no dots there, no dots there, no dots here, you know, less here, you know, this should be about equal to that, that should be about equal to that. Okay, it's just something like that. Okay, so that's great, right? Now number 4. All right, so this is the particle, right? The photon, the particle model, just dots, right, on the screen. But remember, the particle is proportional to the wave, right, or related to. So under your dot pattern, draw some kind of an AX graph. And there's not just one answer, okay? So you want to draw an AX graph. And remember, when you square the AX, you get the intensity, okay? So you can be a little creative. So pause your video and come up with some kind of AX graph. Where you square it, you can have big intensity, no intensity, big intensity, no intensity, gigantic intensity, no intensity, big intensity, no intensity, medium intensity, something like that. Okay, so come up with an answer. Okay, so here you go. Again, it doesn't have to be like this. So, you know, here, you want it to be, so here you're going to square it, right? So you're going to get, you know, not so big, but something here. Okay, here, it's supposed to be 0, so if you square 0, you get nothing. Okay, here, just for whatever reason, I felt like making it negative, because when you square, it's going to be positive, and it's going to be larger here than it is here. Okay, here, it's super bright, so I have this gigantic peak. Could have been down here, who really cares? Here, it's supposed to be 0. Well, didn't quite get that. It's supposed to be 0 here. Then you're going to square that. You're going to get, you know, kind of bright, a bunch of dots. Here's supposed to be 0, and then here you get that. Okay, it's just one possible answer. Doesn't, you know, could have different answers. So that's what you do for something like this. Now, this is not the question we just dealt with, right? This was single slit. Here's the answer for double slit. So for double slit, you know, this is the amplitude, right? And then to get the intensity, you square it, so you just get everything, all these positive humps. And then for where the intensity is large, you get a bunch of dots. When the intensity is 0, you get nothing. High intensity, bunch of dots. 0, nothing. Okay, so this is just another answer. Another example of this business about using this. Okay, very good. All right. I've totally lost my place. That's okay. Okay, very good. Now, quantum mechanics is supposed to be weird, right? Yes. Okay, so let's see how weird it is. All right. So we've been discussing light, you know, the double slit experiment with light and single photons and all that. But now remember what de Broglie said. De Broglie said that if light has a particle-like nature and a wave-like nature, well, so does matter. And then he came up with that formula, that famous formula, which you ought to really memorize. Lambda equals h over p, which is h over mb, right? So this is this mass. So the wavelength of an electron equals that. And we went over that the other day. We saw that Usain Bolt's wavelength is too small to measure, but a fast-moving electron's wavelength is easy to measure. And we talked about the double-slit interference pattern when you do with electrons, right? Okay, so let's see. Here, with photons, we have an equation for a traveling wave, right? For light. This is the displacement of a traveling wave. Okay, great. So we say this is a wave equation, right? It's a wave equation. No kidding. Well, come on now. If photons act like waves and have a wave equation, and we learned that electrons act like waves, shouldn't they have a wave equation? Well, yeah, right? I mean, then come on. If it acts like a wave, it has to have a wave equation, right? So, my gosh, you know? And also, you know, with photons, we had the probability density, which is the probability per length, is proportional to the amplitude squared, right? So this was the particle model, you know, that. This is the wave model, that. Well, gee, with electrons, I see particles and I see waves. So, shouldn't I have something similar to this? Well, yeah. All right. So, wow, what are we going to do? You know? Okay. So, we somehow have to get an equation for the amplitude of the electron matter wave, you know? I mean, you got to. So, okay, that's great. Now, what are you going to do, you know? I mean, if you're developing this theory of quantum mechanics and you're trying to figure out a wave equation and an amplitude of a wave equation for an electron, what are you going to do, you know? Well, what the people did is, you know, they kind of looked at what they did for light, and then they did experiments, you know, and they let the experiments and what they learned with light be the guide. And I don't know what the reason is, but they called the wave equation, oh yeah, I already said that. Okay, so what they decided to do is they called so here's the amplitude of the photon wave, right? So they decided to call the electron wave psi, okay, psi of x, this. So that's uppercase psi, Greek psi, all right? Okay, so the wave equation is going to be called psi, all right, psi of x. Okay, now, for light, oh my gosh, you're going to see this often in this chapter and next chapter. The probability that a photon lands at some value of x within a little width delta x is proportional to the wave amplitude squared times the width, and again that's proportional to the probability, right, times delta x, and that's how we came up with this. All right, agree? All right, so that's great. So we did that, you know, in gory detail, right? This was our great equation. So we got to come up with something for matter, for electrons or whatever, you know. So we're just going to follow it. Why not? Just follow this. So we're going to say that the probability an electron lands at some point x within a width delta x is equal to the wave function squared times that width. That's equal to the probability density. I hope I said probability density up there. Probability density times the width, right? Right? And that says that the probability density is equal to the wave function squared. So see, all we're doing is, you know, copying what we did for light. By the way, I just want to point out one thing. This is probability, right? This is just a number, you know? This is the probability per length multiplied by a length. It's a probability, right? Okay, so all we're doing is we're following what we did for light. And we're going to just follow it, see where it comes up. Now, notice This was all proportions, right? Proportional, right? Remember? Because we said that the intensity was proportional to the amplitude squared. We didn't worry about the equal sign. Well, hey, come on. Let's do it right for matter. We're just going to say it's equal. And I'll explain how we can do that later, but just be aware of that, okay? When we talk about normalizing a wave function, that makes this become an equal, not just a proportion sign. Okay, so this is the proposal for matter. If this is correct, we hope that this is going to be correct. And it turns out it is. Okay? All right, now look at the data. You know, so you see where the dots are not. You see the intensity. So we got to square something, right? We got to square something that gives us this and this. So what function can you think of would work? You know, what function that you know can you square and get something like this and this? So think of some function. There's more than one, you know. How about that? Well, that's going to work, right? If you square it, you just get do, right? That's going to work, you know. How about that? I mean, just for two of them, right? When you square this, you get zoop, zoop, right? I'm done. I don't care about that and that. So all I'm saying is there's a lot of freedom picking the form of the wave function, all right? So there's not just one. But remember, all we care about is this, because the probability density, the probability per length, where the silly particle is, right, per length, is equal to the wave function squared. This is the fundamental thing. Wave function squared. Don't forget that. All right, here's a question for you, please. This is all fake, by the way. This is the wave function of a neutron. At what value of x is the neutron most likely to be found? If you've been paying attention, this ought to be trivial. So pause your video and get ready to answer. Okay, so I assume you've figured out the answer. Okay, remember the probability density is equal to the psi squared. So when you square that, it goes up. When you square that, it's up. Square that, it goes way up, right? So where's the greatest probability? Right there, right there. At x sub c, okay? Because of this. That's what I mean. Probability density psi squared, okay? Now, when we talked about light, you know, we talked about a wave. And we didn't really talk a lot of detail in Physics 221, but in Physics 220 we learned a lot about this. We said, what's really waving? And we learned that as electric and magnetic fields, okay? Oh my gosh, well, we don't have to worry about that now, but I'm just saying, you know, electric and magnetic fields, something was, you know, they were getting, their magnitude was changing and their direction was changing, okay? It's not like a wave on a string. A wave on a string, I mean, something physically is, you know, something, I shouldn't say physical, something material is waving, right? With a light wave, it's not something material, but it's electric and magnetic fields. Now, when you talk about a matter wave, like here, right, a wave function for an electron, what's waving? Well, nothing, okay? Nothing at all, nothing physical, all right? Just a mathematical representation. All right, now, let's keep going. This A, the amplitude of a light wave. You know, you can calculate that from the laws of electromagnetism. You know, I mean, you can. Piece of cake. Well, it's not a piece of cake, but you can do it. So, the question is, how do we calculate the wave function? You know, what law of nature is there that allows us to calculate the wave function? I mean, there has to be, right? Well, there is, and that's the chapter, next chapter. So next chapter, we're going to learn the law of nature, which allows us to calculate this. And it's a second-order differential equation. So, anyway, we'll go through it slowly, don't worry. Okay, now let's just stop for a minute. This is getting crazy. Time out! You know, let's go back to the good old days, right? Newton's theory of motion. Newton said if you start with some x as a function of t, right? So you have the position as a function of t, and then you can use the laws of motion, you know, F equals ma and whatever else you want. And that will allow you to see what happens to the x, right? It allows you to calculate the displacement, you know. Okay, that's cool. Now, quantum physics. I mean, think of a matter particle, you know. But quantum physics, a matter particle like an electron also has a wave-like nature. Okay? So how are you going to come up with an x to describe a particle-like nature and a wave-like nature? I mean, that's tough, right? Because, you know, x for a particle-like nature, that's cool because, you know, the particle is right there. But remember, a wave spreads out. So how can you come up with an x for something that spreads out? That's hard, right? That's hard. Also, again, you know, when you saw the screen of either the photon double slit experiment or the electron double slit experiment, you just saw these dots, and all they allowed you to do was calculate the probability of where the dot lands, right? So, my gosh, wow, what are we going to do? Okay, we got to somehow get probability in here, you know. So basically what we're going to see is that the wave function psi of x takes the place of x. All right, x as a function t. Okay, so this is the variable in quantum mechanics. So basically, so psi of x takes the place of x. Okay, and this wave function, it contains all the information that is available for the particle you're dealing with. Okay? So any physical property of a particle can be determined once you know the wave function. So you can figure out the location, you know, where it landed, probability that is. You can figure out the kinetic energy, anything you want you can get, but you first have to have the wave function. So again, next chapter we're going to learn how you get the wave function. Once you have the wave function, then you can get anything else you want. Okay? So, this is totally cool. This is super important, wave function. That's why we have a whole chapter on it, you know? All right. Now let's just forget about that for a minute. Let's go back to this. All right, so I said I was going to explain this equal sign business here, right? I mean, here we had the intensity was proportional to the amplitude squared, so we just had these proportion signs. But now we have equals. Well, it's not a big deal, okay? It's really not a big deal. What is the probability? So let's go back to this. What is the remember, sorry, this region C here extends out to infinity. Okay? So what's the probability that when you throw a dart, it's going to land in either A, B, or C? Well, it's 100%, right? I mean, 100%. Agree? I mean, the dart has to land somewhere, right? And we're assuming you can throw properly. Yeah. Okay, well, what we want to do here is we're going to say that the probability that the electron lands somewhere is 1. Well, that kind of makes sense, right? It has to land somewhere, right? So that's all we're going to say, all right? We're just going to make it so that the probability that the electron lands somewhere between negative infinity and positive infinity is 100%, is 1. And we're going to do it mathematically, okay? So this is how you do it. So the probability that the electron lands somewhere equals 1. Okay, well here's the math. So the probability equals the probability density, which is a probability per length, times the length, right? And we're going to sum all those probabilities up, right? We're going to sum up the px times the delta x. We're going to sum it from negative infinity to positive infinity. So that's what this means, right? We're summing up the probabilities times the width from negative infinity to positive infinity. And that has to be 1. No kidding. Well, what is the probability density times delta x? It's just the wave function squared times delta x. Whoopee! Okay, so here's the thing. So the wave function is going to have like a coefficient times some function of x. So we have to evaluate this integral and just choose the coefficient to make this integral equal to 1. It's not a big deal. It's just math, you know? All right? So again, we're just going to, so here's what I'm talking about. So let's just say we're going to have psi of x equals like a, I don't know, some function of x, right? So a is better not use uppercase. So a is some coefficient. So we're just going to choose the coefficient. So integral minus infinity to infinity psi of x squared equals 1. Big deal. That's all it is, okay? You're just choosing this coefficient to make this thing work. Now, if you don't like to do integrals, it's got to be a big deal. But if you can do integrals, or maybe use integral tables, it's not a big deal. It's just math. So that's called the normalization condition, okay? The probability somewhere, I mean everywhere, you know, is 1. So you know, we're going to learn next chapter how to calculate psi. And it's always going to be some constant times some function. We have to do this integral to figure out what the coefficient is. And I have to tell you the truth. Sometimes this integral is a pain, but that's life. Okay. All right. Here's a great question. All right, so this is, and by the way, when you get a question like this, you better be careful, you know, to know what's up here. Is it psi or is it psi squared? You got to be careful because you never know what they're going to throw at you, you know, on homework or exam or whatnot. All right, so this is the probability density, probability per length equals psi squared. And this is just x. All right, now you notice that the probability density, it's 0, out to here it's 0 forever, then it goes up here, down here, then it goes 0 forever, right? That's what they mean by that. Okay, so that, therefore, the normalization condition says what? It says that the electron has to be somewhere. The probability that the electron is somewhere is 1. Well, it's not over there. It's not over there. It has to be within here to here. It has to be between 0 millimeters and 2 millimeters. So what does this area have to be? 1, right? 100%. Okay, so pause your video and please you do it. And don't just get, so what you have to do is figure out A. Now, don't just get the magnitude, also, I mean, just don't get a number, get the units as well. Because you're going to be surprised with the units. Really surprised, okay? So stop your video and figure it out. Okay, we're back. All right, so the normalization condition says that the integral from negative infinity to positive infinity is 1. So that just means this is 1, right? So the area of a triangle has to be 1, all right? Well, the area of a triangle is 1/2 base height. So we have 1/2, the base is 2 millimeters. And the height is A, right? A. And that has to be 1, okay? So this 2 kills that 2, so I have 1 millimeter times A equals 1. So A equals 1 over 1 millimeter. So it's 1 inverse millimeter. Okay? All right? There it is. So, I mean, we don't usually have things with a unit of inverse millimeters, right? But that's what it is, okay? But it makes sense, because think about it. The unit here is inverse millimeters. The unit here is millimeters. The area has to be 1, no units. So if you have inverse millimeter times a millimeter, the units kill and you get no units, okay? So this has to be in inverse millimeters, you know? So I mean, it makes good sense, although it's weird. Okay, this is a good place to stop. Let's quit. Okay, now we're going to do some really long examples.